Yesterday we learned the EVT. E in EVT stands for what? Extreme, right? The extreme value theorem. It said if what? If a function is continuous, where? On a closed interval, then the function will have absolute extrema, both an absolute max and an absolute min on the closed interval. There will be an x value that will generate the absolute max and an x value that will generate the absolute min on the closed interval. We then said that those extrema could occur at only one of 2 points. Those absolute extrema can either occur at an x value that is known as a critical value, which is, again, a definition. That's where the function is defined, but the derivative is either 0 or undefined. And or at a what? Endpoint. Good. So now we're going to set off to find the absolute extrema, not from a graph or from generating a graph, but from doing what's called the closed interval method, okay, for finding extrema. So here's what we're going to do. To find the absolute extrema of a continuous function on a closed interval, to find the values guaranteed by the EVT, we're going to identify the endpoints. That's going to be pretty easy because they're usually going to be given to us. Then we need to identify any critical values that live in the open interval. You might have a critical value to the function outside the interval, but you want to find the ones that are just in the interval. Then you're going to find the function values at the endpoints and any critical values, and one of those should be the largest and one of those should be the smallest. That's how you're going to identify the absolute extrema. So you can think of it as a game show right here, right? So I imagine the game show would be called Extrema with 2 exclamation points. Can you see the name of the game show? Let's play Extrema. What do you have to be a contestant on the show? You have to be an endpoint or you have to be a critical value in the interval, all right? So who will be the biggest Y value? Who will be crowned the global max? Will it be contestant A, the ginger? Will it be fist-pumping woman, contestant B? Or will it be creepy guy hunched over the buzzer? C. Which one? All right? Well, let's go ahead and play the game. If you were playing the game here, let's say that the redhead on the left was the left endpoint, the creepy hunched over guy was the right endpoint, and the girl fist pumping in the middle would be the critical value. Once you find all of those 3 contestants, you play the game by plugging their x value into the function, and let's say that these are the y values generated. Which one would be the absolute maximum? Creepy guy, 4220 would be the absolute max, and who would be the absolute min? Fist pump, right? So there's 2 winners. You have the absolute max, the absolute min, and then the other person is just a big nothing. Now, those are the only people that can play the game. So we know confidently then that there's not going to be another x value on that interval that's going to generate a bigger or a smaller y value because they can only occur at endpoints or critical values. All right, let's play the game. Example 7, determine if the EVT applies. If it does, find the extrema guaranteed by the EVT. All right, so we have a function, f of x, it's a 4-3 polynomial, and we're given the closed interval from -1 to 2. Does the EVT apply to this function on the given interval? Yes, EVT applies. And all you have to say is, since our function, whose name is f of x, is continuous on the interval that's given, -1 to 2. So polynomials are continuous everywhere. So if you're given a polynomial in a closed interval, the EVT will apply. All right, so now we know the EVT applies. We have to identify the endpoints. Well, there they are, 1 and 2. Okay, so they're already in the studio ready to play the game. But we have to go out and find the critical values. So how do we find critical values? Right, you find the derivative and you see where it's d and e or 0. So let's find the derivative, f prime of x. That's going to be 12x cubed minus 36x squared. Remember, you want to consider first and foremost every time if the derivative is undefined, because that's the one that students tend to overlook. Is f prime ever undefined? No, it's a polynomial. So there's no solutions from the d and e, so we don't get any critical values from there. Now we say, does f prime ever equal 0? And it's a cubic polynomial, so yeah, it might. So instead of saying f prime equals 0, feel free to actually set what f prime is equal to 0. So now you'll factor out a 12x squared, and you end up with x minus 3 equals 0. So there's 2 critical values. You got x equals 0 and x equals 3. Now there's eligibility requirements to be on the game show Extrema, right? You can't just be a critical value. You have to be a critical value on the interval. Our interval is from -1 to 2. Are either of these on the interval from -1 to 2? 0 can play the game. Welcome to the show. 3, I'm sorry, you live outside the jurisdiction of Extrema. You're a critical value of the function, but you can't play the game. Sorry, maybe try another game show, right? Whatever. Sorry, 3. So now we have team endpoints, -1 and 2, and team critical value, comprised of 1 value. Are you ready to play the game, Extrema? Yes. Here's how you play the game. You just find f of -1, you find f of 2, and you find f of 0. You compute the function value at both endpoints and any critical value on the interval. All right, let's go ahead and let team endpoint go first. Take it away, -1. Play the game. All right, we plug in a -1 up here, and we end up with 3 plus 12, which is 15. Well done, -1. It's not easy going first, but you gave us a 15. Nice. Okay, maybe you don't have to cheer. All right, we'll get a different studio audience. F of 2. Should we let team endpoint go again, or should we let team critical value kind of respond? Let's let team critical value respond. No? Yeah. All right. Team critical value, you go. Plug in a 0. What do you get? 0. All right. Well done, team critical value. You just took away the absolute minimum prize from -1, right? 15 can't be the minimum anymore. Well played. Well played. All right. Now, it's F of 2's turn. Team endpoint. If they want to walk away with both, he should what? Aim high or low? They've already got the maximum covered for team endpoint. Next, 2 should aim low if they want to walk away with the sweep. All right, 2, what is it going to be? Go for it, 2. You get 2 to the 4th, which is 16. 16 times 3, 48. Minus 2 cubed is 8. 8 times 12, 96. 48 minus 96, -48. Oh, and what a fantastic game that was. He came through in the clutch, and he pulled out another victory for team endpoint, okay? So once you have all your y values listed, now all you have to do is answer the question. So F has a minimum of what? Y, yeah, I'll put y equals -48 at x equals 2, and a maximum of y equals 15 at x equals -1. And that's how you would answer it. So the critical value is still going to be a horizontal tangent, but he's not going to be the absolute max or the absolute min. On that interval, this function has a minimum of -48 and a maximum of 15. Pretty easy, right? Pretty easy. All right, and what a fun game it is. I could see this taking off. Oh, yes. It's a critical value, but remember, we're interested in the interval from -1 to 2. And because 3 is outside that interval, he can't play the game. All right? We have to make sure that the critical values are first and foremost in the domain of the function, and then they have to live in the specified interval. All right, example 8. Another episode of Extrema, if you will. Determine if the EVT applies. If so, find the extrema of this on the interval from -8 to 1. All right, so if you want to rewrite this in a different version, it might be more helpful to analyze the domain, the cube root of x squared. We're trying to avoid division by 0, square roots, fourth roots of a negative number, or logs of anything that's not positive. Are we at risk of doing any of those here? No, we have a cube root, so we can have negatives underneath there, but I don't think we're even going to because it's squared. So guess what the domain of f is? The domain of f is all real numbers. Now, any value then that makes the derivative 0 or undefined will be a critical value. Are we on any type of heightened alert here? With the 2/3. Yeah, we're on cusp alert, cusp alert, cusp alert, cusp alert, cusp alert, cusp alert. Run, everybody, we're on cusp alert. And it's Halloween. Yeah, not only do we know we're on cusp alert, but we know that it's going to be at x equals what? What's the root of the base? What when you plug in for x gives you a 0? 0. right? So we know there's going to be a cusp or a vertical tangent at x equals 0 before we even start, okay, because that's the root of the base. But there might be another place where the derivative is undefined and or a place where the derivative is 0. So now we need to find the critical values. Team endpoint is already in the green room eating all the food, -8 and 1. It's going to make them fat and lazy when it comes time to compete. That may work to team critical values advantage. All right, the derivative of 2x is 2 minus 3 times 2/3. That is 1/3, right? X to the 2/3 minus 1, -1/3. Okay, so what we're looking for now is we're looking for a single-termed function. So let's go ahead and rewrite this as 1 over 3 cube root of x. And to get a common denominator, I'm going to scoot this over. This is really over 1, so I'm going to multiply by 3 cube root of x over 3 cube root of x. Okay, what that does is it allows you to get a common denominator. So now, in the numerator, you get 2 times 3, that's 6 cube root of x minus 1, all over 3 cube root of x. Yeah, -2. Why did I put a third there, didn't I? Maybe you should get a different game show host. Yeah, it's -2. That should be then a 2, and then when we get a common denominator, it's just the cube root. All right, there we go. And so now we end up with, that's the cube root of x. We're left with 2 cube root of x minus 2 all over the cube root of x. Very good. When the studio audience starts getting loud, you know there's something wrong. All right, so now because it's a correct, what's that? There's an extra 3 in the bottom. There is an extra 3 in the bottom. Yeah, because that's no longer part of the denominator. Now it's correct, all right? Technical difficulty. Go to commercial. Go to commercial. All right, we're back from commercial. All right, we fixed the technical glitch. This is now a single correct question mark? Yeah? Okay, you sure? Okay, I think so. That's confident. I hope so too. We want to see where the derivative is d and e. And we want to see where the derivative is 0. Now for the d and e, we could set the denominator equal to 0. And as we expected, what value of x when you plug it into the cube root of x gives you a 0? 0. So because that gives you non-zero over 0, that's going to be the vertical tangent, which means it could be a cusp like that, it could be a cusp like that, or it could be a vertical tangent like that or that. Either one of them. That's why we're on cusp alert or vertical alert. We already knew that from the beginning. But now in this case, the thing is equal to 0 when the numerator, or the derivative is equal to 0 when the numerator is equal to 0. So if you solve that, you get the cube root of x equaling 1, and if you cube both sides, you get x equals 1. That's going to be your horizontal tangent. And so that's going to be where the graph either does this, that, or that. One of those 4. But we're in the process right now of finding eligible critical values to play the game. These are both critical values for sure, but which, if any, are in the interval from -8 to 1? They both are, right? 0 is on the open interval. 1 is already included as one of the endpoints, right? So he gets to play for both sides, like full-time quarterback. All right? So now we're ready to play the game. We need to figure out what f of -8 is, what f of 1 is, and what f of 0 is. I'm going to go ahead and list these in increasing order. It might be a little bit nicer to do that. So I have team critical value kind of in the middle, flanked on either side by team endpoint. Now to evaluate it, we're going to plug it into the original function, which is right there. And that's kind of the easier version to use. So when I plug in a -8, what do we get? We get -16. And it's probably easier to take the cube root first. The cube root of -8 is -2. -2 squared is +4. 4 times -3 is -12. So -16 minus 12 is 28. I had room to write it in there. Whew. Plug in a 0, what do you get? You get a 0, and then you plug in a 1, and you get 2 minus 3, which is negative 1. All right? So in this case, the team endpoint, number 1, they already had the minimum captured. He should have gone higher than 0, but stupid idiot didn't play well. He went low again, and so now they're going to argue, okay? You stupid, you should have gone high. You should have gone above 0. I already had the low covered. Sorry, I'm new at this. All right, so that might be the conversation team endpoint would have. But really, these are inanimate objects, so let's just answer the question. So is a good transition word. F has a minimum of y equals what? Negative 28 at x equals negative 8. And a max of what? 0, right? Whoever thought 0 would be the maximum. And a max of y equals 0 at x equals 0. Those are what type of extrema? I'm just saying min and max. So that means what type? Absolute or global. Yeah, very good. Absolute or global. That's what the EVT is guaranteeing. We had a function that was continuous on the closed interval. We are guaranteed to have both the max and the min. So in this case, one of them occurred at the critical value, and one of them occurred at the endpoint. Kind of nice. So it's always helpful when you have the correct equations. So there you go. All right, example 9. Determine if the EVT applies. If so, find the extrema of this function on the closed interval. We have f of x composed of sines and cosines, both of which are continuous on their own for all real numbers. So remember, if you compose two continuous functions, you get another continuous function. So does the EVT apply? Yeah. And you would say something like EVT applies, since or because.
So sorry to interrupt, but I need to make an announcement about the shots. Teachers, if you could check your emails and A through F, can you send those students to the workroom? Only the ones last name first.
Anybody here getting the flu shot on campus?
Thank you.
You are? Oh, okay, but that's A through F, right? So we got to wait. Okay, cool. All right, so now we need the derivative. We got team endpoint already in the house, 0 and 3 pi halves, and we got F prime. It's going to help us find the critical values. So the derivative of 2 sine, don't tell me, is 2 cosine. And the derivative of negative cosine of blob is positive sine of 2x times the chain rule 2. All right, is that ever D and E? Is f prime of x ever equal to D and E? No, no solution for that one. We always consider it first. Doesn't always give us results though. Now I want to know, is it ever 0? So because I'm going to have to work with it, instead of just saying f prime equals 0, I'll set the expression that f prime is equal to 0. And now it's a little pre-cal time. We're trying to solve that trigonometric equation. What do you notice about the angles? Same or different? Different. You have to make the angles the same if you want to solve it. So is it easier to turn a 1x into a 2x or to tear down a 2x into a 1x? Yeah, tear down. Very good. So we got 2 cosine of x plus 2 times beefy purple bracket, the double angle for sine. Sine of 2 times x is 2 sine of x, cosine of x. That's not the first time we've seen that this year. And now we look for a common factor, and in both of them we have a common factor of 2 cosine of x. That leaves us a what in the first term? 1, not a 0. Good. Plus a 2 sine of x. Love that pre-cal, as well as that chicken from Popeye. All right, now we set them both equal to 0. So 2 cosine of x equals 0, or sine of x equals negative 1/2. Can you do it like that? Sure. Yeah. Set it equal to 0 and solve for sine of x in your head if you want to. Now, this is where the interval is kind of helpful because we're solving using the unit circle. We're only going from 0 to 3 pi halves, which on the unit circle starts here and goes around 3/4 of the way. So basically quadrants 1, 2, and 3, but not 4. So where is cosine equal to 0 in quadrants 1, 2, or 3? Yeah, x equals pi halves and 3 pi halves. Do we include 3 pi halves? Sure, yeah. So it shows up as a critical value and an endpoint. And then sine of x is equal to negative 1/2 when x is what? Negative 1/2 is going to be over here when sine and y are negative, and that's the pi 6 reference angle, so it's 7 pi 6. Good. Now in this case, we're only finding the critical values that live in the interval. So we wouldn't include 11 pi 6, right? Even though sine of 11 pi 6 is negative 1/2. So now it's time to play the game. So we come all the way back up here, and let me give myself more room this time. Remodel the studio. There we go. And now we'll go f of 0. The next value that we're going to get to is pi halves, so I'll put them in order. It's kind of nice to have them in increasing order. Pi halves, and then we get f of 7 pi 6. And then finally f of 3 pi halves. So the endpoints are flanking the two critical values. And now for the first time, the teams are evenly matched, right? 2 critical values, 2 endpoints. Playing the game, you can play the game in any order. In fact, you don't even have to think of it as a game. Just evaluate the function. So with y'all's help, because you see how I'm doing today, what is f of 0? You get sine of 0, which is 0, minus cosine of 0 is 1. 0 minus 1 is negative 1. All right. And you can almost imagine hearing clapping in the background. Well done, 0. Pi halves. Plug in a pi halves. Sine of pi halves is 1 times 2 is 2. Minus. When you plug in a pi halves into the second term, you double it right away and you get cosine of pi. So minus cosine of pi. Cosine of pi is negative 1. So I get 2 plus 1, which is 3. So far, each of those guys are winning. X equals 0 has the absolute min prize so far, and pi halves has the absolute max. And we'll go to a commercial break and see if the 7 pi 6 and 3 pi halves can do anything about it after we return from our break, which is a message from our sponsors. I'm going to abandon the game show thing. Okay, good. 7 pi 6. What's sine of 7 pi 6? Negative 1/2 times the 2 is negative 1 for the first term. When you plug in a 7 pi 6 into the cosine of 2x, you double it and you get 7 pi thirds. 7 pi thirds is coterminal with what? Subtract or add back a full rotation. Subtract a full rotation. It's coterminal with pi thirds, right? 6 pi thirds is 1 rotation. So remember, coterminal angles have the exact same trig ratio. So cosine of 7 pi thirds is the same as cosine of pi thirds. And what is cosine of pi thirds? 1/2. So negative 1 minus a half is negative 3 halves, or negative 1.5. So far, he's the low point. Now when we plug in a 3 pi halves, sine of 3 pi halves is negative 1 times 2 is negative 2 minus cosine of 3 pi halves times 2 is 3 pi. 3 pi is coterminal with 1 pi. So we end up with negative 2 minus cosine of pi is negative 1. We get plus 1. That puts us back at negative 1. So love that trig, bless you. So it looks like the biggest value is 3 and the smallest value was negative 3 halves, which means it looks like team critical value, well, never mind. No game show. We'll just answer it. So F has a max of y equals what? 3 at x equals pi halves. Sometimes they'll ask you for the maximum value. Sometimes they'll ask you for the location of the maximum value. So I'm just answering both of them. Be prepared to, though, answer specifically what is being asked. And F then has a min of y equals negative 3 halves at x equals 7 pi 6. So irresistibly, now that we're done, I can't help but say team critical value swept on this game show. And team endpoint goes home with like a consolation toaster or something. right? The loser contestants always get something. All right, there you go. Pretty fun to play the EBT game. Pretty easy to play the EBT game, right? It's almost like you're not even using calculus at the end. You're just evaluating functions. The only calculus involved is in finding the critical values that live in the interval, okay? Sweet. So what do you want to do if you want to find extrema, the absolute max and mins, and you don't have the graph and the EBT does not apply? If the EBT does not apply, then you can't do this method right here. But as we saw yesterday, just because the EBT doesn't apply doesn't mean that you can't have absolute max and mins. We saw that on example 3. So without the graph, how would we determine where the absolute max and mins are? Well, generating a graph would still be helpful, right? Plus, using any other tool that we've kind of developed along our mathematical careers would be helpful, right? So use it all. Use it all. So that's what example 10 is going to be doing here. Find the extrema of each of the following functions over their domain by sketching their graphs. All right, first things first, let's find the domain of this function. We know we don't want to divide by 0, and I'm at risk of doing that here. And we know we don't want to take the square root of a negative, and I'm at risk of doing that here. So if you remember from pre-cal, we had questions like this. You can quickly find the domain by saying the radicand in this case has to be strictly greater than 0. By keeping it from equaling 0, that means we're not going to get division by 0. And of course, now we know the radicand can be positive. That is a quadratic inequality. We can't solve it algebraically. So we solve it some other method like graphing. This is the point 0,4. It opens down, and the x-intercepts are what? You can probably look at it and tell. 2 and negative 2. Good. And now I want to know for what values of x is that thing above the x-axis. That's going to be right in here. So it should be everything between negative 2 and 2. So your domain is exactly that. Your domain of f is the set of all x such that negative 2 is less than x is less than 2. What graphical features do we have then at 2 and negative 2? What do you get when you plug a 2 in? You get 1 over 0. And if you plug a negative 2 in, you also get 1 over 0. So remember, non-zero over 0 means that there's a vertical asymptote there. Now, if you plug in a negative 3 and a positive 3, now you're not getting 0 in the bottom. You're getting a negative under the radical. That means it's an imaginary. But that will tell you then what the graph kind of looks like at the edges here. You have vertical asymptotes. What about any symmetry? The asymptotes look like they line up across from the y-axis from each other. Is this an even function or an odd function or neither? Remember, the test is if you replace x with negative x, do you get the same thing you started with, or do you get the opposite thing you started with? If you get the same thing, it has y-axis symmetry and it's even. If you get the opposite thing, it's an odd function and it has origin symmetry. Plugging in a positive x or a negative x here is irrelevant, right? You get the same thing. So it has to be an even function. So it has y-axis symmetry. That's kind of good to know. Because I know the graph cannot look like this now. Because that would not have symmetry. It's either going to open up on both sides and have an absolute min, or it's going to open down on both sides and have an absolute max because of the symmetry. All right, let's pick up a free point. What's the easiest point to get for any function? When x is equal to 0, the y-intercept. Plug in a 0 and you get 1 over the square root of 4. That's 1/2. So we got 0, 1/2 right here. Now let's see if we can find the x-intercepts. How do you find the x-intercepts of a function? Set the whole thing equal to 0. Well, because it's a fraction, the fraction is equal to 0 when the numerator is equal to 0. So that's going to happen when 1 equals 0. Even on a day like today, Halloween, if 1 went dressed as a 0, does that make it a 0? No, it's still a 1 on the inside. 1 is never going to equal 0. So do we have any x-intercepts? No, we have no x-intercepts. And that is enough to tell us what the graph looks like. Because of the symmetry, this graph has to open up on both sides. And it would have to look like that. It can't open down, because if it opened down, it would cross the x-axis. But wait, it could look something like this. It could look like a W. If that were the case, then 1/2 wouldn't be the absolute min. You'd have an absolute min over here and an absolute min over here, symmetrically. How can we determine if it looks like the blue one or the purple one? I like the derivative answer better, right? Because the derivative, if we set it equal to 0, will tell us how many horizontal tangents we have. And in the blue case, we'll have 1 horizontal tangent. In the purple case, we'll have 3. So let's go ahead and find the derivative. Now, to take the derivative, in this case, I would recommend bringing the whole quantity to the top and saying it's to the what power? -1/2, using the chain rule instead of the quotient rule. So here we go. F prime of x is going to equal -1/2, 4 minus x squared to the -3/2, times the chain rule, -2x. If you then simplify the -1/2 and the -2, divide out, you're left with x in the top all over the square root of 4 minus x squared cubed. Now, how many horizontal tangents does f have based on the derivative here? In other words, if I set f prime equal to 0, how many solutions is that going to have? 1. That's going to be when the numerator x is equal to 0. And because there's only 1 horizontal tangent line and it happens at x equals 0, I know it doesn't look like the purple case. It looks like the blue case, and there's the horizontal tangent. So now, with all of that information at my disposal, I can now answer the question about extrema. F has a min, right? A minimum of what? Yeah, of 1/2 or y equals 1/2, if you want to do that, at x equals 0. Does it have a max? No, there's no max. Now, we also know that y equals 1/2 is not only the absolute minimum, but it is also a relative or local minimum. Yeah. Okay, so that's how you would sketch something like that. Use all the information that we've learned about our whole careers. The only thing we needed the calculus for was just to determine then what the absolute minimum was. Okay, now for this one, this is a piecewise function. So hopefully piecewise functions you could sketch a little bit easier. It's part parabola, part line, and it switches at 1. So what's the domain of this function? Parabolas and lines domain is everything, and at 1 it's defined at 1. So it should be all real numbers, right? So let's go ahead and sketch it. The most important x value is 1. What's the limit as x approaches 1 from the left? 3. Is it a solid dot or an open circle when I graph it? Solid dot, because it's less than or equal to. And then, of course, 5 minus 2x squared, that's going to end up being a parabola that opens down. So it's going to look something like that. And here's the maximum vertex at y equals 5. What's the limit as x approaches 1 from the right-hand side? 3, right? And has a slope of positive 1, so then it goes off at a 45 like that. So that one was a lot easier to sketch the graph of. Does this function have a max or a min? Very good. No max and no min. Of course, we mean absolute and global. Does it have any local extrema? Yes, it has a local max of what? Of y equals 5, good, at x equals 0. And it also has a local min of what? Y equals 3, good, at x equals 1. Is this function differentiable everywhere? No, it's not differentiable at 1. There's a sharp turn there. So just with a little bit of effort on the graph, you can answer a whole slew of questions related to calculus, non-calculus questions. So no absolute max, no absolute min, but certainly has a local max and a local min. It's unbounded above and below. All right, any questions on example 10? We're moving and grooving today. All right, now it says sometimes we need to use the calculator's number crunching ability to find X-intercepts for us. So this is one of the things you should be using your calculator for, and that is to solve equations. So if you want to grab a calculator, you can, or you could just kind of watch, look on up here with what we do. As soon as my calculator loads, we'll get to it. Let's read what it says while we're waiting. It says, using your calculator's equation solving capability and not just its max-min ability, find the extrema of this function on the interval from -1 to 1. All right, so while my calculator is loading, is this function continuous on this closed interval from -1 to 1? Yes, right? It's made up of continuous functions. E to the negative x is continuous, 2x is continuous, 1x is continuous. So does the EVT apply? Yes, the EVT applies. So because the EVT applies, we are going to find it using the closed interval way. So we already have team endpoint, -1 and 1, in the studio ready to play. We just need the critical values, right? So we're going to need the what? Derivative. Let's go ahead and find the derivative of f. F prime of x then is, by the product rule, 1 times e to the negative x. Will someone grab that? Plus x times, thanks Clancy, times the derivative e to the negative x is e to the negative x times -1. There's the product rule, -2. Good, I'm not even needed in the transaction. Tyler answered the phone. Here's our one right home. All right, so product rule. Derivative x is 1, second goes for the ride, plus x goes along for the ride, times the derivative e to the negative x, which is itself, times the chain rule, -1. Don't forget that little -1. And then minus the derivative of 2x is 2. Is this ever undefined? We always consider that first. No. For the same reason the original function was continuous, the derivative is continuous, so there's no solution for the DNE. But is it ever equal to 0? Maybe so. The only thing is I cannot solve this one using algebra. It's not a real easy way to do that. So this is where your calculator is going to be helpful. You can, since we have the derivative, you can graph the derivative and find where it's equal to 0. And in that case, I'm just going to say f prime equals 0 instead of writing out the entire expression. That's going to earn a check for your method. Now we'll go to y equals, and we'll clear out all of this stuff. And I'll come up here and carefully type in the function. E is second ln, and that automatically puts you in the exponent to the negative x, plus x, e to the negative x. I guess I could simplify that and call it minus, bring the -1 out front, minus x times e to the negative x again, and then -2. And because I want to know where that's equal to 0, I will graph a 0 always in a second y, because your calculator can find intersection points a little bit easier or faster than it can find zeros. Now, we want to make sure we're only finding the critical values that live in the interval from -1 to 1. So on a calculator, you have the advantage of being able to specify your window. So let's go ahead and specify the x-min to be -1 and the x-max to be 1. That way we're not even tempted by other critical values outside the interval, right? If you don't know they're there, you're not even tempted by them. Now, because we're looking for the x-intercept, I like to keep my y-min, y-max to something even smaller than -10 to 10. I like -5 to 5 or even -3 to 3. What that does is it stretches out your y-axis. Okay, because sometimes you'll have a graph that looks like it may cross, and you'll have to zoom in. If you go to -3 to 3, you're stretching it out enough to know if it crosses or not. And we hit graph. Boom, there it is. There's one critical value. We find it by hitting second trace, not number 2, which you could do if you didn't graph 0. we're going to use number 5. So it says, is this the first curve? Hit enter. Yep. Is this the second curve? Yep, hit enter. And then for your guess, you could just hit enter. There's only one. If there were more than one, you'd want to scroll closer to the one you're interested in, but just hit enter, and there it is. So it gives you the point of intersection. So that is the other critical value, x equals, or the critical value, negative 0.374. Now that is a number that goes on and on and on past the third decimal. So here's what we're going to do. We're going to get out of there and we're going to go to the home screen. If you hit the X button and hit enter, there it is. Your calculator automatically stores from the graphing screen the X value in X, and if you had alpha 1, that's how you get Y. It stores the Y value. But if you go back to the graphing screen and use it again, it's going to overwrite this X. So what I would always recommend is restore to something else. So hit X, stow, and then alpha A. And now it's in there as alpha A. A is never going to get written over automatically unless you do it yourself. So now on your iPad/paper, if you stored it as A, call it A on your paper/iPad. And now we're ready to play the game. We want to figure out what is f of -1, what is f of A, and what is f of +1. Now you could plug those back into the original function, but what I'm going to do is again use my calculator. So now I'm going to go back to y equals. I'm not going to delete that in case I need it again for another part of the problem. I'm just going to go down to y3, and I'm going to type in my original function, x e to the negative x, and then minus 2x. There is the original function. Remember, by the way, that your calculator could have graphed the derivative if you would have then taken the derivative of this in y3, but we found the equation pretty easily. So now I'm not interested in the graph of that. I just know I have my function in y3, so here I go. I recall y3 from the home screen. Alpha trace, number 3, I want to evaluate it at -1. So open parentheses, -1, close. You can write that down. That's negative 0.718. You're still responsible for 3 decimals in your interim analysis. Now you can recall and scroll back and over the -1. You don't have to find them in any order. Let's just find it at 1. I'll delete the negative and I get negative 1.632. And then recall it, second enter, and come back and change 1 to alpha A. Right there. And you get 0.204. So once you've written all of those down, and notice in my analysis, I actually put f of A. Because I called it A right here, I can refer to it as A here, and that's another reminder to yourself to use the actual value that you stored. And now by the EVT, one of those is the biggest and one of those is the smallest. So f has a max of y equals what? 0.204. Good. At, now in this case, don't say at x equals A, say at negative 0.374. Don't put A as your final answer, but in the interim you can use that. And similarly, f has a min of y equals negative 1.632 at x equals 1. So that's how you want to use your calculator. Now notice, if you were just to graph y3, it looks like that. Your calculator can actually find the absolute maximum right here for you. But College Board or I would never ask a question where you could use your calculator to find the maximum without taking the derivative, okay? But just know that that's an option if you want to check. Second trace, number 4, scroll to the left of where you think the high point is. I'm actually on the wrong curve. There you go. Toggle up and down to switch curves. Enter. And then I'll toggle to the right until I know I'm coming back down. Enter. And then enter for your guess. And there it is. It actually finds the maximum numerically. But that's not going to benefit you in any way except to check your work on your homework. You're going to find it by taking the derivative by hand or graphing the derivative and then finding its x-intercept. All right, so there you go. That's how you do that one with the calculator. And that looks like that's the last one of this section.